And my name is Isabella Lambardia. This is my take-home exam for process dynamics and control. Here we have our first problem with a continuous stirred tank reactor. So for part D, I first want to point out that we know our system is two first order processes because it's given that it's a continuously stirred tank reactor. And so we know that typically two first orders in series does give over critically damped systems, but our system differs in the fact that our transfer functions are not in series, but in parallel. And we know that because if they're in series, that means that the output of one transfer function would be the input to the other. But here we have our two outputs being the height and the temperature of the tank being driven by the same input, which is the mass flow rate in. And while we can see in our transfer function that we do have a real time constant, this transfer function is actually made up of our two first order transfer functions. So we can see that whenever we do factor out the denominator, we end up with complex conjugate poles. And that's what allows our system to oscillate. And we did calculate zeta, our damping coefficient, and by definition, if zeta is between 0 and 1, it is an underdamped system, and we got a zeta of 0.169, so we know our system must be underdamped. So here's my block diagram. One of these transfer functions would be from the mass balance and the other from the energy balance. For problem 2, we're dealing with two tanks in series. And one of them is a surge tank, so there's a weir. I do just want to point out that the flow rate through the weir is not constant. It is dependent on H1 and H2. The inputs to the system are mass flow rate, and our outputs are height 1 and height 2. So for part E, it asks us to explain how each of the three heights would vary with time in response to a positive pulse change. And the way I like to think about this is a pulse change is like dumping a bucket of water into the inlet flow stream. So it increases increases rapidly, and then it goes right back to the nominal steady state value. So just to clarify, H1 and H2 are dealing with the weir, H1 being the height on the first side of the weir, and height 2 being the height of area 2, and H3 is the tank without the weir. So if we imagine that we're dumping a bucket of water into the inlet stream, we're going to see that H1 initially overshoots its new steady state value and then slowly decreases until the new steady state value is reached. And we know it overshoots because our 0 is greater than our pole. So we find that our tau A is greater than our tau. So that's how we know it's going to overshoot. And like I said before, the flow through the weir is not constant. So whenever we have a higher difference, the water is first dumped in, we're going to have a higher difference between our H1 and H2. So that flow rate through the weir is going to be higher, and it's going to decrease with time. So the height is going to initially decrease at a faster rate, and then with time it will slowly steady out to a higher steady state value. And as H1 is draining, it's going to drain into H2. And same thing, the flow rate through the weir is going to have a higher rate at first. So it's on a the H2 is going to increase at a faster rate in the beginning, and then it's going to slowly come to a higher steady state value. For height 3 without the weir, because we are dealing with the pump, our flow rate out is set, so it's going to jump to a new steady state value, a higher height, and then it's just going to stay there. So if these were step changes, then we are dealing with an integrating process due to that pump. So if there's a step change in the input, our mass flow rate in, that does not mean that there's going to be any change to the flow rate out. So we would see all the heights would linearly increase until overflow happens. So to sum it up, like I said, the system is a second order process, with our input being mass flow rate in and our outputs being H1 and H2. And we know that in our first transfer function, our 0 is greater than its pole. So it shows that an overshoot will happen in H1. And like I said, the pump does make it an integrating process, so our heights are not self-regulating. And I said that a surge tank would be beneficial in the case of small fluctuating inputs, like fluctuations in the input, because the surge tank has a pole, which creates a filtering effect. So as we maximize this filtering effect, it's going to slow down the response time of the system. So, which is good because our pump is going to pump at the set rate no matter what. So just to protect the pump, we want the least amount of, we don't want the pump to feel all the changes in the input. So by maximizing the tau 3, our filtering effect, it's going to basically just make it easier on the pump and protect it. However, since we do have an integrating element in this process, I did say that if there are large fluctuations in the input, it might not be a great idea, because we have this amplification effect, which is our tau 2 over tau 3. So as the input changes, it's going to have an amplified effect on the output, or H1. And if our area isn't big enough, then we could see an overflow easier. So we'd have to we would want to minimize the amplification effect and maximize the filtering effect. So in order to do that, we would have to set the areas equal to each other. Because if you think about it, if you have a smaller area of that H1, the faster it's going to overflow. So we want to make sure that area is big enough so to avoid overflow, but to still maximize the filtering effect. So in order to do that, we should split A1 and A2 so that A1 equals A2 and that equals A over 2. So